So our target in this video is to write, graph, and interpret exponential growth functions. Okay, so pretty much every time we're going to start with some sort of real-world scenario with these type of problems. In this case, we're talking about a population of tigers. So just in case you're having trouble reading it, it's a little small this time. It says a population of tigers is increasing in number by 15% every year. So 15% every year. The last data was collected in January 2005, when there were 3,200 tigers. Okay. And the question that they want us to answer is, how many tigers would you predict there are now? And now being January 2013. Okay, so the first thing we can do is use our exponential growth model. The model that we created in class using the flu virus data that we generated was y equals a, where a is the starting point, times 1 plus r being the growth rate, times to the x power, where x is the number of cycles or years, whatever the case may be. So in this case, we're talking about y is the total number of tigers, a is the initial number of tigers, r is the growth rate, and x is the number of years. They said it grows 15% every year, so that's why we use the number of years in this case. All right, so let's plug in all of our numbers. Back to our initial problem, they said we had 3,200 tigers to start with. Our growth rate was 15%. Now, we're not going to put that as 15. We're going to convert that percentage into a decimal, which as a decimal is 0.15. And then the number of years is 8 years. And I got that by just subtracting 2005 from 2013. It's been 8 years since January 2005. Right. Now that we have a function with all of our data plugged in, all we have to do is go ahead and evaluate it. So first thing we need to do is parentheses. 1 plus 0.15 is 1.15. We just did that right there. Now, before we multiply these together, we have to do exponents. Remember, it's parentheses, then exponents, then multiplication and division. So, we're going to do 1.15 to the 8th power and get approximately 3.059. Just keep as many digits as you can there, and we'll round it off at the very last step. And then multiply last. So 3,200 times 3.059 gives approximately 9,788. And I did round that down because you can't have, 0.8 tigers or 0.6 tigers. So I rounded it down to 9,788. Now that we have our answer, we've made our prediction. There's going to be about 9,788 tigers in the year 2013, in January. We want to analyze the graph. Okay, so first thing is I want you to pause the video for a second here, copy this down on graph paper if you have it, and then fill in the rest of the chart. Go ahead and figure out how many tigers there'll be after 1 year, 2 years, 3 years, 4 years, and 5 years, and plot that data on the graph.
So we also want to take a look at the data on the graphing calculator as well. Now to do that, we're going to go to y equals, type in our function, y equals 3,200 times 1.15, close parentheses, to the x power. There we go. Give you a second to get that in. And you're going to hit graph. Notice it doesn't appear to be graphing anything. That's because our window only goes from -10 down here to +10 up here. But think about what our y-intercept is. Our y-intercept was 3,200. So we need to adjust the scale of our y-axis. Well, the calculator lets you do that. If we just go to Window, this button right here, now we want to make the Y minimum a little bit less than 3,200, so maybe we start with 3,000. Go down, make the Y maximum a little bigger. Maybe we go to 6,000 there. Okay, now we don't want the Y scale to count by ones because it's going to be too hard to see those ones if we're plotting 3,000 of them. So maybe we count by 500s on the Y scale. Let's go back to our graph and see what that looks like. Aha, there we go. Now we can see the y-intercept here and watch it curve up. Okay, if we want to analyze this graph, we can use the trace button right here and move around. It starts us out on the y-axis, at the y-intercept rather, of 3,200, and we can push over to the right and verify that when we get to x equals 1, we're right around 3,700 tigers. Check your data to make sure that's correct. And we can go to 2. Get as close to the number as you can. We're right around 4,200 tigers there. For 3, it looks like we're right around 4,850 tigers, and so on. Now, if you want to view this data also as a table, the calculator will do that for you as well. All we have to do is, instead of hitting graph over here, notice right above it, it says table. So we hit second graph. That gives us the table. Okay, so for 0, we're at 3,200. 1 is 3,680. Check your data. You should notice the same numbers in the table that you've already calculated. The calculator will do that for you if you just remember second graph. That'll give you the table. Now, of course, it's all dependent on getting the correct function here. If you have the incorrect function, the graph or the table won't look right.
Okay, and one final question. Let's say the population of tigers doubles every year. What I want you to figure out and just be thinking about for next time, what percentage of growth would that be? In this case, we said the tiger's population grew by 15%, and so we called that 0.15. Well, if the population doubles every year, you're doing times 2 every time. What percentage of growth do you think that is? And a little hint, if you think back to the activity we did during class, it'll be the same number as the flu virus. The amount of people infected with the flu virus doubled every cycle, didn't it? So whatever R we used for that should be the same R here. And then think about what percentage of growth that is. That's it.